Welcome to all of you who are attending our Darwin lecture for the Friends of the Flaxmill Maltings. We are going to wait a little bit longer for everybody to be able to join us, but you're in the right place. If you have any queries, just put them in the Q&A and we will get to them at the end of the talk. I'll just give it a few more minutes. Thank you for joining. Well, we've reached 7 o'clock and welcome to all of you who are attending our Darwin talk from the Friends of Flaxmill Maltings as part of the Darwin Festival. We did something last year and we even did something, I think, face-to-face the year before, but it's a really nice opportunity to reach out to people, not just in Shrewsbury, but further afield as well. It's lovely to see some of our own volunteers online as well, which leads me to introduce our speaker for this evening, which is Richard Bonella. He is one of the board members of the Friends of the Flaxmill Maltings. We have been in existence since 2010, and our aim is to bring the Flaxmill Maltings to life, but there's lots of things that we can do beside that. One of those is to talk a bit more about industrial revolution and the evolution of the power for industry. So, Richard, over to you, please.
Marianne, thank you. Well, and good evening, everybody. Looking at the list of names, so I can see your names, but not your faces. There are some I recognise, so clearly there'll be no escape from this. Well, my own background, first of all, not a professional historian. I hasten to point that out because we do have such present. I come to this from an engineer's point of view. I spent 25 years as an aircraft engineer in the Royal Air Force, including a stint at Shawbury, hence living in Shrewsbury now, and then 20 plus years as a physics teacher. When I was roped into helping it with the Flaxmill, I rapidly realized that it really is quite an amazing structure, and the engineering of it interested me considerably. What it no longer has, of course, is the power supplies, the power sources that were in use when it was a Flaxmill, and that's rather a shame. But when asked if I would say something for the Darwin series of lectures, it did strike me that one could perhaps look at the way that these power sources for industry in general, both for making things and for moving things, have evolved, if you like. So that's really what I'm going to look at tonight. Okay, I plan to talk about the principles of power systems rather than giving a rivet by gasket account of these things. I want to consider the concept of evolution and to what extent does it apply to the way that power systems have developed over the years. It's perhaps worth noting that the word evolution is very widely used nowadays, and I'm not sure that it's always appropriately used. For example, in my days of teaching A-level physics out at Concord College, I was never very comfortable in talking about the evolution of stars. There might be an element of natural selection in how stars get on, if you like, because a small star with a large neighbor next to it may not survive very long. But on the other hand, the development of stars, I think, is now reasonably well understood by some quite interesting methods, and it's encapsulated in the wonderfully named Hertzsprung-Russell diagram that some of you may be familiar with. And this diagram points to something which is fairly close to the clockwork universe, even if we don't quite understand yet how all the components work. It would seem that new forms of stars are not appearing year by year and evolving into something different. So evolution in the universe, evolution of stars, not sure that's quite such a good use. So how does it apply, or will it apply, to the development of systems for powering the making and moving of stuff? Now, I don't really want to go into the ins and outs of the subtleties of evolutionary theory. I'm not qualified to do that. I want to take the idea of evolution as I think it's generally basically understood. That is that changes can happen from one generation to another in living organisms, coded into their genes, and these changes may or may not be beneficial to the survival, to the flourishing of that particular species at the time in the environment in which it lives. So does that sort of notion apply to the development of power systems? Well, let's have a think about it. First of all, is the invention of new power systems a random process? Did steam engines actually spring from a chap watching a kettle boil in his mother's kitchen and thinking, I know, I could power the Flying Scotsman with one of those? Perhaps not. Did two American bicycle makers sit down one morning over breakfast and say, tell you what, let's build an aeroplane? Equally, perhaps not quite as simple as that, but we'll look at these things. And what about the reasons then for new methods thriving or fading away? Natural selection, as it applies to living things, has one key difference, I think, from the natural selection that perhaps applies to our modern human inventions, our technical systems. Natural selection for living things works on the environment as it is at the time. It really can't look ahead. And perhaps in the past, that was broadly true also of people building power systems, devising ways of powering human activity. It's not true now, because we are now in a position of looking ahead at climate change, a notion which I think finally is broadly accepted, and thinking, well, it's not good now, and it's going to get worse unless we do something. So we're looking now at our power systems for both making things and moving things in the light of what will happen if we don't change, rather than what is making us, what's encouraging us to change now. So we can come to again to details of that later on. But let's go back. We're going back into time when what we now know is based on archaeology, physical archaeology, on what I suppose might be called genetic archaeology, not on direct witness records, no original sources, nothing that you can go to a library and consult. But where does all this start? Well, if you want to make or move something, the simplest thing is to do it yourself. And so perhaps 100,000 years ago, somewhere in Central Africa, an individual could knap, that is chip, flints into useful tools, and having done that, could pick them up, carry them a modest distance to where they were going to be used or bartered for something else. And the same do-it-yourself approach might apply to other things, hunting animals, early growing of crops, perhaps even in the right areas, drying out of salt crystals for sale, and so on. But somewhere, and I think archaeology now points to the area that's roughly modern Kazakhstan, about 5,500 years ago, humans began to domesticate horses for a variety of purposes. And certainly horses couldn't make things, well, other than the obvious that horses make, but they could assist in the moving of things. And with some ingenuity, they could begin to power things as well. They could certainly pull plows and carry loads. Other animals in other parts of the world are used in a similar sort of way. Camels, for example, seem to be domesticated in southern Arabia, I understand, about 3,500 years ago. Interestingly, in Central Asia at high altitudes, the domestication of the yak apparently goes back a long way. And this is really based on genetic analysis of the way that yaks living in close proximity to humans began to change by comparison with their neighbors living in more remote areas. And that goes back some 5,000 years, maybe longer. Well, certainly we can't attribute the domestication of those animals to any one individual, perhaps even to any one small group. We don't know the circumstances that brought about the idea of doing it and made it possible. But what they do perhaps is give us a baseline on which we can calibrate later inventions that we do know a good deal more about. At this point, I'd like to start looking a little bit at the words we're using here and agree the words we might use to describe the performance of power sources when we're thinking about how they have evolved. Now, sitting putting this lot together, I was reminded quite forcibly of times when, as a school teacher, I realized sitting looking at the class in front of me, you could divide them into three groups and not necessarily of equal size. I was probably, I would hope, communicating reasonably well with the middle group. There was another group who were frankly baffled because I'd already gone too fast and lost them. There was a third group who were bored because they knew it all already. Okay, so awful warning for how I stand tonight, but nonetheless I'm going to plow ahead because I'm talking and you can't stop me, okay? Right, so first of all, what do we mean by this word power in the context of transport manufacturing? That's to say, moving stuff and making stuff. Power is the rate at which we do work, or the rate at which we transfer energy, if you like, same thing. And so a more powerful machine can do work faster, can transfer energy faster. or a more powerful heater can increase the temperature of things more rapidly, and so on. We do then need a brief mention of energy, because I've just done it, okay? And this is always a fun task for a physics teacher, because your students, teenagers, arrive with all kinds of ideas about what the energy word means. Well, despite the myriad ways in which it's used in everyday speech, energy is not any kind of material stuff, okay? We can go back a couple of centuries to the hunt for caloric and various other things. Energy is not a material stuff, but nor is it a mystical entity, despite what the advertisers of various commercial products might want you to believe. Energy is a human idea. It's the result of a calculation, okay? It's a quantity that we can calculate. And we can calculate it in many different situations. And when we have an acceptable way of calculating it in a particular type of situation, we tend to give it a name. So, for example, we can calculate the amount of energy for a mass that is moving. And that amount depends on the size of the mass and how fast it's moving. And that's the form of energy that we generally now call kinetic energy. Okay, we can calculate an amount of energy for something which, if you could let it go, or if you did let it go, would move in response to a force. Okay, and that's a potential energy. Force between two magnets will give you that sort of energy, but the most obvious practical everyday example is gravitational potential energy. We have to do work to lift something up against gravity, and in some way or other, we might get that work back again if we let the object fall, harnessed to something suitable. If you think about that lifting process a little further, you might have done that with a machine, and maybe the machine was powered by a motor which ultimately burnt some fuel, and you've used the chemical energy from the fuel to add to the gravitational potential energy of the object. If you let it go, it will move in response to gravity, and it will acquire kinetic energy, whilst reducing its gravitational potential energy. So these forms of energy all sound a bit airy-fairy, a bit physics teachery, but actually, they are the kind of things that if you're going to build machines to do things, you've got to be able to calculate reasonably well, because you need to know what's going on. Humans can transfer energy, can do work, but quite modestly. Horses can do better, and modern machines can do it better still. And we're beginning to look now, of course, at why do we have these modern machines? Well, because they are superior to horses, even though horses are perhaps much more fun. Pursue it a little bit further. If you consider this business of moving things in terms of energy and power, if you follow the stages of a process, some sort of manufacturing process, at each stage you should be able to calculate this total quantity of energy appearing in stored or evident in various ways, if you like, including, of course, the energy which is wasted by heating things up to no particular purpose. But the total amount of energy, stage by stage, should remain constant, and that's what we call conservation of energy. Okay, it is actually important to us in manufacturing because it means I can't end up with more energy than I started with. So depending on what the energy requirements are to do something, I've got to have that much available to do it. Equally, I can't get energy through or out of a system in the long term any faster than I can put it in. Okay, you might think back to the cameras that we don't see so much of these days, the kind where a battery used to charge up some sort of storage to make the flash work, and you heard a little whining noise. It took a while to store up the energy you needed, and it was all then used very rapidly in a flash. But until it had restored, you couldn't flash it again. Okay, all right, I know modern camera phones have kind of almost got us away from this. We don't notice it anymore. But the arithmetic of conservation is very important. We cannot use what we haven't got. So let's go back then to the sorts of power that humans have used. Okay, and I'm moving now beyond horsepower, let's say, or beyond the power of horses. I'd like to look a little bit at wind and water. Now, I think largely used for recreational purposes, for fun, but they've gone through their times in which wind power and water power were tremendously important to us. Water, as we shall see, can not only be used as a power source, but improve the effectiveness, the efficiency of other existing sources. Let's start first of all with moving air, what we call wind. Okay, and this can provide power for machinery and for transport. The devices by which we transfer energy from wind to something we want to move, they go back a long, long way. Ship sails, which are made of animal skins or some sort of cloth, okay, certainly go back several thousand years. And we know that in Egypt, for example, thousands of years ago, boats made out of bundles of reeds had primitive sails, and that was quite a good system. Those sails would be quite primitive. They would be a square rig, basically adapted to run before the wind. So if you wanted to go back the opposite direction, you pretty well got to wait for the wind to change or shift it yourself. Okay. Development of these sailing boats, well, that's an area in which the Chinese were ahead of us for quite a while. Chinese sailing junks had really good steering rudders, waterproof compartments, and so on, at a time when these things were really quite novel notions in Europe. But by the 15th, 16th century, and certainly on into the 17th and 18th century, more elaborate designs of ships in Europe allowed ships to run much closer to the wind, or run almost across the wind, so as to be much more flexible and semi-independent of the direction of the wind. And perhaps the culmination of ship design, we might think of the T-Clipper, the Cutty Sark, if you've been on that recently since they rebuilt it after the fire. Very, very elegant ships, but nonetheless they required a reasonably strong wind to move, but not so strong as to overwhelm them. So they were somewhat at the whim of the wind, if you like. What about power for manufacturing things? Well, again, windmills have been around in Europe for the best part of 1,000 years. The idea, I gather, imported by travellers from the Far East who saw what was happening in Eastern Asia. Used for things like grinding grain, and you could fairly say that grinding grain is a manufacturing process. The wind's more powerful than humans, and unlike a horse, it doesn't need feeding. So windmills, generally a good idea. And windmills have gone on being used. Pumping water, still in remote areas. You think of the Western movies with that rattly old windmill pumping up the water because there was no mains power laid on out there. And today, windmills driving the turbines that are increasingly generating electricity for us. And I think gradually people are getting used to the fact that they are there, and they're being built offshore, of course, so you don't actually have to look at many more of them scattered across Welsh hillsides. So we've gone on using wind power even up to today. What then about moving water? Well, at the simplest, you can carry things on moving water if the water's going in the right direction. Things like floating logs downstream to a sawmill. Okay. Or put them in a barge and float the barges downstream. If you want to do better than that, well, perhaps put the barges on a canal where the water surface is scarcely moving and tow the barge along. Initially towed by people, but rapidly, wherever possible, and this probably requires a decent tow path and some investment, towed by horses. And that way you've got really quite a much improved transport system. And perhaps this can be something we can put into numbers. My slide, and there are slides, a handful of slides to those who are worrying. Marianne's going to put the slides up. Just some numbers to compare different ways of carrying things. And I suppose, what are we looking at here? We're looking here into 18th, 19th century technology, aren't we? Pre-railway, if you like, that a human might pick up 50 pounds. Now, I know this is a pretty notional human, but a horse might carry a couple of £100, depending on the size of the horse. Put that load into a cart, and I understand the rule of thumb is that, generally speaking, the horse will pull about 10 times as much in a cart. Depends, of course, on the state of the roads, and that's where the argument for things like macadamized roads, part of the turnpike system, comes in. If you put those goods onto a barge and thereby almost eliminate the friction, okay, the human who could carry a 50-pound pack can, I gather, carry something like 35,000 pounds. I'm quite staggered by that, but I did dig around. There's several sources seem to confirm this. I have to confess, my experience of pushing barges is limiting to punting one of those old timber sailboats on the East Anglian Broads. And there we were pushing a pole, and we were assisted by a sail, and we weren't in a tearing hurry. But the same argument then says that a horse pulling a barge would shift something like 100,000 pounds. Not rapidly, and you need relays of horses to do this, but you can go on shifting that stuff pretty well 24 hours a day if the barge is happy to do that. And notice here, these are only figures for the load that you can shift. We haven't at this stage, or haven't looked at how far you can go in 24 hours. We haven't compared the range of a human walking a few miles with the range of a horse. Okay, so barges then, generally powered by internal combustion engines now, continued into use well into the 20th century. I can just about remember seeing some of them on the canal system around London. Now, of course, they are almost exclusively recreational vehicles here, I think, in the UK. But you've only got to cross the Channel and see the barges going up and down the Rhine to realise that barge use is still quite a significant thing in Europe. What matters, of course, is that you have a cargo that doesn't deteriorate. Perhaps something like coal or grain or building materials, where as long as you feed it into one end of the system, it comes out of the other and it hasn't gone off on the way. So in summary then, wind and water can provide us with power or facilitate the provision of power. I'm thinking about the horse towing a barge, well beyond the capability of a human. So we can see factors that would encourage the use of wind and water. Right, I now need to make the second of my little diversions into physics teacheriness, if that's a good word. The table of loads, which we had up a moment ago, used a unit which was certainly still very much in use when I studied for my degree in aeronautics, although that was a while ago now that I'm forced to think about it. As a modern physics teacher, Brexit notwithstanding, I should certainly use a different unit. But the unit used back in the day was the pound. And I've used that because it's what the builders of canals and barges would have used. The first thing to say about the pound is that, strictly speaking, it's a measure of mass and not of weight. Okay, I warned you this is physics teachery stuff. And mass is how much stuff there is in something. Okay, weight is how much force there is between that stuff and the planet that we will happen to live on the Earth. Okay. For example, an astronaut traveling to the moon on arrival at the moon is much the same astronaut who left. Their mass is much the same. Their weight is substantially different because the gravitational force per unit of mass on the moon is much, much less because the moon's smaller. Okay, so a difference then between weight and mass. So strictly speaking, we shouldn't say that something weighs a pound. We all do, or it weighs a kilo, if you like. Okay, it's really not a problem in everyday life because we know that if it has a mass of a pound or a kilo, my more modern units, we know what the weight feels like. We know how much force we have to apply to pick it up. Okay, and we're not likely, most of us, to have to carry it around on the moon, I guess. But once we start to think about machines which are moving things around, then we do need to think about mass. Because if you want to think about accelerating something so it's moving, the force that you need to apply depends on the mass of the object. So we do perhaps need to be thinking sometimes about these as units of mass rather than of weight. Okay. The system that the world mostly uses now, as I say, unit of mass is the kilogram. And again, forgive me, grandmothers and eggs, but a kilogram is a bit more than 2 pounds. Okay, another unit which I need to drift into, which again is not part of the modern system, but actually is still in very wide use, okay, is the horsepower, when we're talking about the power of things. Introduced by James Watt, he of the steam engine, and perhaps not the kettle, and he introduced that unit about 20 years before our Flaxmill was built, and he was working on improving steam engines, not inventing them, but improving them. And he made what was probably the single most significant improvement to the plumbing of the steam engine, because he was, as a skilled instrument maker employed by the university up in Glasgow, he was asked to repair a model steam engine, and he looked at it and thought, there's a better way of doing this. And his concern was the amount of water that was used in the steam engine to cool down the steam after you'd made it and put it into your cylinder to get the steam to condense, to contract down again. And he essentially thought there's a better way of doing this, namely the separate condenser. And that's what he invented, that's what he patented, and that's what made him and his partners like Bolton and so on, as in Bolton and Watt, a great deal of money. The horsepower survives as a unit. Bit of a slippery one because different technologies, different disciplines define it differently, and there are different ways of measuring it. And so if you're comparing devices and the detail really matters, you need to look into that and make sure that you are indeed comparing like with like. But rough ideas. If you look at the power of your car, you will probably find it quoted in horsepower as well as in kilowatts, which is the modern, the international system equivalent. Okay, and in round figures, 1 horsepower is about 3/4 of a kilowatt. Somewhere in the handbook of your car, stuck away in the glove compartment, you'll find 2 numbers that bear that out. Watt had in mind a horse, hence the name horsepower, and Watt's hypothetical horse could lift a mass of 550 pounds to a height of 1 foot in 1 second. And if that again sounds a bit as though Watt was a physics teacher, he wasn't, lucky chap, but he had in mind a horse turning a horizontal wheel with a rope attached and lifting weights up in a factory or out of a mine or whatever. And that was his standard horse. It was, I think, quite rapidly pointed out that very often the horses actually used for that kind of thing were little ponies, little mules, and they were not as powerful. So a pony or a mule power might only be 3/4 or half of a horsepower. But the horsepower has survived. Modern metric units, we would roughly say it's a mass of 250 kilos lifted through a height of 30 centimeters in 1 second, and that's where the horsepower comes from. Don't worry, that I will not be asking questions on this at the end, but it's just to give you an idea of what we're talking about. Okay, so the units that we need then, knowing that the pound and the kilogram are units of mass, and knowing roughly what the horsepower is and where the idea came from, because modern systems, their power output still quoted in horsepower, and I shall do that to you once again with one more table of numbers, only one, promise. Okay, so I mentioned what the steam engine, and that brings us from horses and wind and water onto probably the single greatest step forward, okay, and that is the invention, the introduction, the application of steam engines. Here we've got developments recorded in a much more modern way. There are documents, okay, perhaps not documents to modern standards. They are people's personal accounts. They are other people's accounts of what they thought happened, rumors and so on, but nonetheless a great deal better than simply trying to reconstruct things from shards of pottery and bits of rusted metal. Now, the working steam engine was undoubtedly the result of the insights of a great many people over a long time before it was a practical device. I'm picking out just a few. I hesitate to cite Wikipedia, but the Wikipedia article on steam engines is actually great fun for the sheer number of people it lists as contributors to the notion. Pick just a few. End of the 17th century, so this is not the start of it by any means, because the notion, the principle goes perhaps back to the ancient Greeks and so on. End of the 17th century, Thomas Savery, using the pressure differences between boiling steam and condensed steam to pump water out of mines. He claimed that he produced a machine which could do the work of 2 horses. Well, it's not huge, is it? But it didn't need feeding, and they would work, if the machine continued to work successfully, 24/7. Whereas your horses, actually, those 2 horses needed to be part of a much bigger team to rotate them through. In practice, his boilers and his pipe work were not very successful. His joints weren't pressure tight. Interesting notion, but not a huge commercial success. Excuse me. A decade or so later, Thomas Newcomen, a name perhaps better known, produces a much more robust and practical steam engine, and that used the rocking beam system, and that began to pump water out of mines, and later adapted to turn shafts. And so by the time we get into the 18th century, that sort of engine with rocking beams powering factories. And I think we can be reasonably clear now, looking at our own Flaxmill, the first steam engine in there, the space assigned to it had sufficient height that there was likely to have been a rocking beam across the top of that. Not later ones, but the first engine house built to accommodate a rocking beam engine. So, is this an evolutionary process? Well, I think it is, because the idea had been around for centuries. People have sketched and scribbled and drawn ideas, but they were generally toys, okay? And so Savery's ideas go back to Denis Papin, and Papin in turn had gone and picked on the ideas of Christian Huygens, and Huygens, of course, is a name better known perhaps for his invention of the pendulum clock and his work in optics. But all these people building on what somebody else had done before, and as there was a chance to experiment, as metallurgy got better, they were better able to make a practical working device. So Newcomen builds these pumping engines. They're widely adopted, but they have this constant need for large amounts of cooling water. And that's where James Watt appears in the story, because he added his separate steam condenser and thereby significantly reduced their steam consumption. His notebook is in the Library of Birmingham. You can actually see records, and certainly there are copies of it online, in which he noted down, described experiments he did, what he was trying to achieve, and where he got to. But incidentally, the story of him watching his mother's kettle seems to be apocryphal, contributed, I think, by a cousin of his, because he's quite clear in his notebook where discussions with other people as an adult had led him to consider what might be done to improve steam engines. The fact that he was an instrument maker and had access to manufacturing facilities meant that he could actually put these ideas into practice. So we've got that business of a lot of people contributing to the development of steam engines. But what would encourage that? What would be the external factors, and what would be the natural selection that would promote steam engines, if you like? Well, this is the time of the rise of industrialized manufacturing, okay, and particularly of textiles, and particularly certainly in this country. You think about wool and cotton, and latterly, of course, flax, as in our own mill. But to do this industrialization, well, you need large buildings. like our flax mill. Okay, you need a cheap and biddable labour force, women and children. Blunt, but there it is. Okay, and they've got to be capable of using the machines. The machines in turn have got to be capable of doing at least part of what was formerly done by hand. So you've got to have someone to invent and build machines like looms and so on. And all these things need a source of power. And if you go look back to the 18th, early 19th century, there's not really a lot of competition for sources of power. In some places, given the right topography, given the right rainfall, there's running water running down hillsides, and some of the towns in Lancashire and Yorkshire have that sort of asset. We didn't in Shrewsbury. It was coal-fired steam engines or nothing. The steam engines in turn, of course, need coal and water themselves, and coal and water can be provided by a canal. So have you got a canal? Well, yes, here in Shrewsbury, just as the mill was being planned and built, a canal was being dug into Shrewsbury from the coalfields over in what is now Telford to bring coal into the town. The canal builders realised there's a prime customer putting a factory up on their doorsteps, and they actually diverted the route of the canal slightly to ease the unloading process to make their product more attractive. And other factors, as I say, I mentioned improvements in metallurgy. But in some ways, it's a virtuous circle, isn't it? If you get a wide range of people who can use your steam engine, whether for pumping water in mines or for manufacturing processes, and then for transport, you put it onto rails and so on, you're going to make a lot more steam engines. Makes the whole enterprise more profitable. It makes the research and development work worth undertaking, and so on. And so we can start to think about steam engines powering transport, railway engines, traction engines, ships in due course, and even airships. Not a major customer there, but airships in the 19th century, a few attempts at powering them with steam engines. An image, if you like, okay. If you can call to mind what is officially the nation's favourite painting, the Fighting Temeraire, there's a sailing ship. Now, I mentioned the Temeraire because apart from being famous and doing its bit at the Battle of Trafalgar, the Temeraire was laid down pretty well at the same time as our flax mill was being built, the last decade of the 18th century. When the Temeraire was towed away, nearly 40 years later, to be broken up, rather sad, the ship that's towing it away, and this is in Turner's picture, is a steam tug. So the grand old lady of sail is actually being hauled off to the breaker's yard by a little dirty, smelly, polluting, noisy steam tug. That's progress, if you like. And so by the 19th century, steam engines are oh, brilliant. Haha, Temeraire, lovely job. Thank you. Okay. By the 19th century, we can begin to see sail giving way to steam as far as shipping is concerned. For a while, ships have both. You think of some of Brunel's ships, but eventually it becomes apparent that a good supply of coal is really all you need, and you can pretty well cease to worry about sails. So those factors all contribute to the rise of the steam engine. Maybe they also contribute to its later fading away, to its demise. Because in the second half of the 19th century, and we'll come on to this, internal combustion engines appear in increasingly reliable and practical forms. And each offers some significant advantage over the steam engine. So these various applications which have used steam engines begin to fade away or begin to slide sideways into using internal combustion engines. But before I leave steam, I think it is worth perhaps looking at how steam improved on horses. Thanks, Marianne. This is the second table of numbers. I did say there are only two, but these are the power outputs from various steam engines. They're in horsepower, the unit which I snuck under your nose earlier on, so you can directly compare these to what a horse might do. Savoury, the chap with the leaky boilers and pipework, offered an engine good, he claimed, for the work of 2 horses. By the time Watt has got his hands on Newcomen's engine and introduced the separate condenser and all the rest of it, he's initially offering something which will provide 10 horsepower. You can see quite a jump there. Our Flaxmill steam engine, I understand the first one put in there, South Engine House, a power output of about 20 horsepower. Came, I think, from Bolton and Watt in Birmingham. Just by comparison, a modern lawnmower is already 5 horsepower, and a modern small car is 100 horsepower. Okay. So you can see that the engines used in our flax mill really not a great deal of power, An aside to that is that perhaps explains the presence of flywheels. If you go to visit somewhere like Bliss Hill, where you can see these engines in use and sometimes fired up, the biggest single object very often that greets you as you walk up at the engine is an enormous flywheel. That would take some spinning up. There's a lot of inertia in there, but once spun up, would considerably smooth out the power delivery from the system. So if someone connects a loom which was not previously connected, the whole system isn't going to grind to a halt. Flywheels to smooth out supply of power, an important consideration. Oh yes, at the bottom there, they're railway locomotives, an A1 class loco. This I just happened to find. This was an article about the newly built replica of an A1 class loco, the Tornado, which does run about the place. Sometimes we hear them here in Shrewsbury. You can tell there's one there because everyone's hanging over the bridge looking at it. But that's 2,400 horsepower. And the modern large loco, this is a Russian loco, which I know very little, but I assume they're used for crossing the large distances of continental Russia, up to 17,000 horsepower apparently, which is quite impressive. So just to give you an idea, again, there are not exam questions at the end, but you can see the scale of development that went on within steam power there, if you like. Okay, now these numbers, or some of them at least, might look pretty impressive, but they do score rather poorly on a different measure, and that's efficiency. And here I mean efficiency as the ratio of the useful work done by the steam engine, that's moving stuff about, to the amount of energy transferred into the engine. That's the chemical energy of the coal. And the sad fact is that on engines that were mobile, steam engines, and probably didn't have space for a condenser, at least not in the early ones, efficiencies would be less than 10%. Okay, much of the wasted energy goes straight up the smokestack in the hot exhaust. As you might say, room for improvement. And even a well-designed and maintained static engines with condensers might only achieve 30%. Some of this is, of course, a matter of thermodynamics, and one of the great developments of 19th century science was thermodynamics, and it is said that it was driven originally by this question of, if you buy a pound of coal, how much work can you get out of it? And so really quite theoretical concepts, ideal engines, Carnot cycles, all that sort of business, stem from a practical consideration of what's the best we can get out of burning a pound of coal. And the answer turns out not to be all the chemical energy that is in there. It's actually to do with the range of temperatures in the engine, the difference between the highest temperature that you reach and the lowest temperature, which is usually ambient temperature and so on. And those limits actually still apply to things like modern jet engines. We'll come to that briefly later on. Okay, so let's move then away from steam onto the internal combustion engine. The clue's in the name, internal combustion. Okay, the fuel is burnt with the gas that you're going to expand to drive the engine. Okay, steam engines burn their fuel outside and then heat up water in a separate boiler. Internal combustion engines, smaller and lighter. Okay, and they waste less energy by heat loss in this process of pushing steam around. So what about the invention and the development then of internal combustion engines? Well, the steam engines separated the hottest part of the structure, where you burnt the coal, from the point where it had the highest pressure, the steam boiler. In an internal combustion engine, those things are the same place. In your car, in the cylinders, the fuel is burnt, and the pressure rises as the fuel burns and expands, or the gas that it's in expands rather. So that has implications for making these things. You can't really have an internal combustion engine until your metallurgy is sufficiently good to allow the machine to survive. Okay, engine blocks still quite frequently cast iron because it's hard wearing and so on, but you have to cast to a higher standard, I suspect, well, for certainly, than our iron masters cast the Flaxmill. Clearly our Flaxmill, fortunately not having flaws, more serious flaws in the metal, but you'd have to cast an engine block to a higher standard, and that requires a greater understanding of metallurgy. The other material for engine blocks, aluminium. Well, aluminium wasn't available as a separate element until well into the 19th century, but by the back end of the 19th century, you could have an aluminium engine block if that's what you wanted. Again, like the steam engine, these internal combustion engines, lots and lots of predecessors back in the 18th century. They were essentially, it seems, some people seem to refer to using small explosions to push things along. Familiar, I guess, with firearms, with cannons, the idea that you fire a gun, something, a bullet or a shell comes flying out one end, you've pushed it along. If those explosions were smaller, repeated, controllable, then you could push the moving parts of an engine. And so early prototypes including ones running off powdered coal. They played around with hydrocarbon fuels, liquid and gaseous. They played around with hydrogen. By 1807 in France, and the French seemed to be quite well ahead of this, there was a boat powered by an internal combustion engine. By 1813, an internal combustion engine powering a truck. Not that it went very far, but the principle had been established, if you like. By the 1830s, static internal combustion engines powering water pumps, which again goes back to where the steam engine had started a century or more before. Well, these things so far experimental, but not really commercially viable. Commercially viable internal combustion engines, right? The great names. What we would call a petrol engine is actually pretty well an Otto engine. Okay, Nicholas Otto in 1876, and the engine that we call a diesel engine was indeed the result of work by Rudolf Diesel. Okay, differences between these characters. Well, petrol engine, the Otto cycle. Okay, you have to ignite this mixture of fuel and air with an electric spark, which has the advantage of perhaps it's more controllable, but you have got to get it warm, and all the rest of it starting it is maybe more problematic. In a diesel engine, the air is already compressed to the point where when you squirt the fuel in, it ignites of its own accord, which is great, as long as your petrol engine doesn't do the same trick. Diesel engines running at higher pressures to get that temperature rise when you compress the air, higher temperatures, higher pressures, heavier engine blocks, and that has the result, which I think we're all generally familiar with. If you think diesel engines, you tend to think trucks, maybe taxis. But of course, in recent years, diesel engines have been made light enough and small enough to fit in cars as well. Diesel engines, yeah, very robust, reliable, really. Reliable perhaps because of the lack of electrics. The great problem nowadays, diesel engines are regarded as dirty and polluting, so an early target for emission control measures and so on. And if you're paying your ultra-low emission zone charge in London, it's not a good idea to have an elderly diesel. So, end of the 19th century, we have got various versions, and there were others, but the petrol engine, the diesel engine, seem to survive, come out on top of internal combustion engines. We might note in passing that they're possible because manufacturing processes exist which in the early days would have been done in steam-powered workshops. Steam-powered machinery originally makes the things that you need to build the early petrol engines, even if the steam-powered machinery is then superseded by internal combustion engines. Well, advantages then for internal combustion. Well, they're burning liquid fuel generally, so you don't need to shovel coal. And there goes the job on the railways. More importantly, and this is, sorry, physics teacher again, but there is more energy per kilo, okay, in a kilo of liquid fuel than there is in a kilo of coal, okay. Probably about 2/3 again as much for petrol or diesel compared to a high quality anthracite type coal, and maybe 3 times as much as there is in a cheaper nasty brown coal or lignite. So you can see why, if you have to shift your fuel about and it has a mass in pounds or kilos, it is useful to have something which mass for mass does more work for you than the old coal system. And you could say now, if we had something that was even better, and there is, but it was affordable, usable, we might well move to that, and more of that in a few minutes. You might then say, well, why would you burn these fuels? They're better. Why not burn them in existing steam engines? Well, I've already looked at the question of size and weight for steam engines. Steam engines, fine for trains, fine for static installations, obviously, not so good for cars and trucks. Okay, they did exist, but history intervenes, and this is human history. End of the 1920s, the Great Depression seriously reduces the amount of freight which is moved around in the developed world. By the time the depression is over, economies are recovering. People are looking and saying, well, if I buy a truck rather than paying to have my goods shipped by train, that truck is a great deal more flexible. And a figure I found actually researching this talk, which has staggered me, by the end of the 30s, pre-World War II, in UK alone, there were almost 500,000 goods vehicles, petrol-driven goods vehicles, an enormous boom in those vehicles. And again, as ever, economies of scale, they get relatively cheap to produce. And I suppose just the factor, because I'm talking about industrial uses, but parallel to this, of course, the growth of private car ownership again means the makers of cars and of petrol engines have got a ready market for a larger number of their engines, more units. So again, keeping costs down. We should include in our internal combustion engines the other kind, and that is the gas turbine. I'll come on to that in a moment, but let's just think, what would push the development of aircraft travel? Well, certainly both world wars encouraged the development of aircraft as they then stood, both World War I, World War II. The aircraft by 1918 were a great deal more powerful and robust than those in 1914. And certainly over World War II, the jet engine, which had existed as a concept in the 1930s, literally, forgive me, takes off. And Germany and Britain and the Americans are flying jet aircraft by the end of the war. This had been foreseen by the Wright brothers, my two American bicycle makers. They had a history as makers of things. They were young lads in their 30s, but they were designing, building, repairing bicycles. They knew how to do that kind of thing. They had seen the demonstrations of sorts of flying machines which were popular in the 1890s, and they had realized that what was missing from all these things was to put together the twin elements of the powered aircraft and the controllable aircraft. And that was what they set out to do. They really were bright chaps. They realized they needed an engine the sufficient power to weight ratio, light but powerful to do the job. They calculated what they needed, and they got someone to cast them an aluminium engine block. And they achieved that. Okay, this is an aluminium alloy engine. It weighs 180 pounds, and it produces around 12 horsepower. Okay, so that sort of fits in those numbers at the top of my horsepower table, if you like. Not very powerful, but good enough to do the job. The other thing that they did, incidentally, along the way, having built themselves a small wind tunnel powered by a fan to test shapes of wings, they pretty well designed the modern propeller as we know it, because the old airship propellers tended to be flat plates bolted together at angles. The modern propeller is very much a credit to the Wright brothers, and people have since looked at what they did and assessed it with much more modern, sophisticated methods, find out that it is a pretty good piece of kit. Okay. So these aircraft then, they were the original application of this other form of the internal combustion engine, the gas turbine. Gas turbines, why those? Well, they do have advantages over piston engines, although the early ones obviously experimental and expensive to make. But a higher power to weight ratio again, and you can see why that would be important in military aircraft, in fighter aircraft, and better performance in the low density air that you find at high altitude. And so when World War II is over, they start to appear in civil aircraft as well. And now, once the gas turbine, which is the core of the thing, if you like, is established, it not only powers jet aircraft, it powers helicopters as well, but it powers ships and trucks and electrical generating plant all over the place. There's another aspect perhaps also to think about with gas turbines. For quite a while, they were the province of enthusiasts, and the struggles of Frank Whittle to get his notions accepted here in the UK, well understood. The first aircraft jet engine, I think, actually really should be credited to the German O'Hain, but he too didn't get much support for it until war broke out. So initially, not necessarily adopted with enormous enthusiasm. They too would depend critically on metallurgy. This is where we do get into this business of theoretical efficiencies. Within a jet engine, you're burning fuel, your turbine blades are getting pretty hot, but the temperature which they reach compared to the outside air temperature is the fundamental defining factor of the ultimate efficiency you can get out of that engine. It is never going to be 100%, but the hotter you can get those turbine blades to run without failing, the more power you'll get out of that engine. And so that's where we get into metallurgy again, and of course into ceramic blades and so on. And it's still very much a driving force in the development of aircraft engines. On the other hand, and this is where I come back to my point about perhaps natural selection in this human system looking forward, the emissions from aircraft engines becoming much more and more questioned. There was a time when it was only the noise they made. You might recall the problems that the Concorde aircraft had. No one was really questioning, I don't think, the muck coming out of the back of those 4 Olympus engines. They were questioning the noise. Nowadays, we're questioning the exhaust coming out of the engines. And so the aircraft manufacturers are having to look to other fuels. Are there other fuels there that they can burn? Yes, there are. Hydrogen has actually got a much better specific energy, that's energy per kilo, than those hydrocarbon fuels. but you have to liquefy it and probably keep it cold, and we need the infrastructure to do that. But we may yet see hydrocarbon powered aircraft. The other route, of course, is electrically powered aircraft, and I think the way things are going, we may find that the lower and slower aircraft are electrically powered, but we'll have to come on to electrical stuff in a few minutes. Okay, so electrically powered engines in general, history of electrical technology, if you like. Well, the first battery, Alessandro Volta, 1800. The first electric motor, our own Michael Faraday in 1821. Again, half a century or more before practical systems become available, and the first electric trains, electric trams are 1879 and 1881, and these are both courtesy of Siemens and the first electric train system in Berlin. Why electric trains again? Okay, if you can reliably build electric motors following the principles established by people like Faraday, well, apart from anything else, you've got the basis of the Siemens company. But why would they be worth doing? Well, quieter, cleaner. If you're going to make trams powered by trains, you're replacing horse-drawn trams, with obvious advantages of cleanliness and reliability and all the rest of it. If you're going to run railways, long distance railways, electricity, advantageous over carrying all the fuel about, because you're not carrying all that fuel. Your power comes down electric cables, but you do have to lay those electric cables. And so what you tend to see, I think, in general, is that countries with a fair amount of wealth, countries which are reasonably compact, countries where railways are state-owned, and so there's an inclination or greater inclination to make the investment than if the railway companies are competing private companies, tend to be more electrified. And in Europe, the most highly electrified country, and perhaps in the world, I think, as a proportion of its track miles, is Switzerland. Here in the UK, we are somewhat below the European average in terms of percentage of track miles which are electrified. And from what I read, I gather they have a similar question in the States. They could now electrify on a much larger scale, but it's very expensive to do, and who's going to cough up and pay for it? Incidentally, along the way, if we're thinking electric trains, we in the UK have a lot of this hybrid, the diesel-electric train, where a diesel engine burns liquid fuel to turn a generator to produce electric current to run an electric motor to power the train. Advantages in the handling of the train from that, but pollution-free, noise-free, it ain't. And I offer in evidence standing on those underground platforms in Birmingham New Street while somebody is running the loco rather than getting it out of the station. So I would say we really can't count diesel and electric sets as proper electric trains. But in the towns, yes, electric trams superseded horse-drawn trams, but they did require the power supplies through the rails or through the cables. Electric cars, yes, they go back to the 1880s. They were electric cars. Once you had reasonably reliable accumulators, batteries, you could charge them up and you had electric cars in the UK, in Europe, and in the USA. Again, something I discovered, apparently Ferdinand Porsche, he of the Porsche cars, in 1898 produced a hybrid electric car, a concept which is being bandied around now. Electric cars, clean, quiet, easy to start, and so on. So why did they not thrive? Why are we now trying to get rid of internal combustion engines and go electric? Well, the answer seems to be price. Henry Ford's Model T was less than half the price of a similar electric vehicle. And that ratio is not much dissimilar now. I don't know if any of you bought electric cars, but you go out and buy them. At the moment, electric vehicles tend to be more expensive. Although I see the Chinese have produced if you like, a Chinese version of the Trabant almost. Perhaps that's being unfair to one or the other, but a basic electric people's vehicle. And so we can, I think, expect the price to come down. There's also the question, if you have an electric car, of how to charge it, which has a funny, familiar modern ring to it. But if you look at a large country which doesn't have an electrified countryside, as it didn't out in the 1890s in the United States and large swathes of Europe, if there are no electric power stations in your neck of the woods and you don't have an electric supply, you can't charge an electric vehicle. So when Henry Ford offers you a Model T at a sensible price, you buy the Model T. So we have, again, quite a complicated set of factors, contemplated interplay of factors, if you like, on the selection of type of vehicle, internal combustion versus batteries. suppose we might just say now, if we look at the current leaping forward, what will electric cars depend on to be adopted? Well, falling unit costs, if possible, greater energy density in the batteries, how much energy both per kilogram of mass, because you've got to carry it around, but also cubic meter, because you've got to stuff it under the floor. And those things are rapidly improving. And if you're really bored one day and start to look at recent improvements in battery technology, batteries are coming on quite rapidly now because there's money in it. Because it's not just tiny batteries to go into your mobile phone, and you think how much more compact they've become in the last 2 decades or so. It's larger batteries to power your car or truck as well. But lastly, almost with electricity, not transport, but manufacturing, making stuff. And here, electricity pretty well rules the roost, doesn't it? Electricity can turn machines, it can heat ovens and furnaces, it can move conveyor belt systems around, and it can power your computers. No small consideration in modern automated manufacturing, stock control, all the rest of it. Here in Shrewsbury, our own Flaxmill actually had electric machinery, which seems to go back to the 1920s. Up in the top of the hoist tower, underneath that coronet, if you're local, remains of electric machinery with makers' marks on, which I think, as I recall, as well, some while since I've looked at it, are getting on for a century old. And electric powers here, there doesn't seem to be an alternative in the offing. I don't think we're about to have another great move forward. I can remember a brief time, back in the 1960s and so on, when there was talk about using compressed air for computing devices. Can you imagine a pneumatic computer? It was quite serious. There were serious articles in Scientific American about the design of switches and storage and so on, using little jets of air. It's gone very quiet on that front, I think, pretty well. So electricity, yeah, here to stay. It offers a flexibility far superior to steam engines or even petrol engines turning crankshafts. They're noisy, dirty, smelly, all the rest of it. This is natural selection at work. Okay, so conclusion then. Well, a mad gallop through history. Thank you, Marianne, for those slides. Is there an element of randomness in how these developments come about? Well, I think, yes, there is, in that lots of individuals have contributed to things. It's very easy to write some individual down in history as the father, I'm afraid usually the father rather than the mother, of some technology. You don't have to go very far, even dare I say to Wikipedia, before you find out that all kinds of people contributed all sorts of bits and pieces to these things. Why did they contribute? They spotted a requirement, they had an idea to which they could apply something they thought of. They had reasonably advantageous circumstances. This used to mean that they were either clergymen with 6 days a week free, he says, ducking, or that they were fairly moneyed. If you were female, of course, you had to pretend to be a husband normally to get yourself published. People like Caroline Herschel and so on are perhaps quite rare in having their names known. And of course, Marie Curie. Incidentally, if you ever teach Polish students, do try to learn it, and I've forgotten it now, but Marie Curie's Polish name. It's wonderful. Yeah. They had to have these sort of advantages which would allow them to pursue an idea that they had. You have to wonder how many ideas didn't survive because the person who thought them up wasn't in a position to do anything about it. But also, as I've tried to say, if you have an idea, you have to have the physical means of implementing it, so that you really could only build electric motors when you had the kind of technology that steam engines had made possible, and so on. What about natural selection? Well, yes, again, and I think those influences come and go. In nature, we might look and say, well, what naturally selects for something? Sometimes we can see, moths change color in industrial environments. We now know to our cost that viruses adapt pretty darn quickly to measures to suppress them. And if you have a population which is not vaccinated, the viruses can make merry. And that which is most transmissible or most infectious or whatever tends to come to the fore. Same sort of process, except we have this business of foresight. And I think that's an important consideration now, at least. We're looking ahead and saying, well, here's a new technology. We don't need it now, but it actually might be quite a good idea in years to come because. Or in some cases, yes, we do need one now because of what's happening in years to come. And that, I think, provides a driving force that's maybe not there, or isn't there in nature. So, yeah, I think we can say the development of sources of power for making things and moving things is a reasonably evolutionary process. And before I get cut off, and whilst I've still got you, do come and see the Flaxmill when we get opened in the summer, and let us show you some of what we're talking about. And if you've got that steam engine kicking around the garden shed, if you don't want it, please do bring it in and we'll install it. Okay, thank you very much indeed, folks.
Thank you very much, Richard, for that. I will stop recording.